The talk right now that you're in is Reflections on Trusting TrustZone by Dan Rosenberg. Rosenberg.
Thank you. All right, so as he said, I'm Dan, and today we're going to be talking about attacking TrustZone. So hopefully if you're in this room, you've heard of TrustZone before or have some idea of what it is, but just in case, TrustZone is a system-wide approach to security implemented on ARM devices, which enjoy a sort of majority market share, especially among mobile devices. And TrustZone allows these devices to implement a fairly wide range of security-related tasks. It accomplishes this by segregating all software and hardware on the device into what are referred to as the normal world and the secure world. So in the normal world, you have all of the components of your traditional operating system, including your standard applications, system services, and the operating system kernel. Now today we're going to be talking exclusively about an implementation on Android, so this will include the Linux kernel, for example. Then in contrast, on the other side, we have the secure world. Now there are a number of different design models for implementing a secure world, but the most popular in practice is having a secure operating system kernel, or a TrustZone kernel, under which a number of potentially independent trusted applications, or trustlets, may run. And these can run concurrently and are frequently written by third parties to implement various modularized pieces of security technology. Now, access between the normal world and the secure world is mediated by a monitor component. And the secure world has complete access to all of the hardware and software on the device, but the normal world does not. It can only communicate with the secure world via carefully defined channels. So the secure world is capable of designating certain regions of memory, for example, as secure only, and the normal world, even with higher privileges like kernel privileges, cannot access those secure memory segments. So it's acting much like a hypervisor in this case. In my experience, the most common usage of TrustZone is for DRM, digital rights management, where the basic use case is protected media content can be sent to a user's device and then decoded exclusively in the secure world. So even if the user has full control over their own operating system, all of this decoding takes place in a protected environment that the user does not have access to prevent piracy. Additionally, TrustZone is used frequently for other secure key storage applications, such as for dmVerify, which is the Linux kernel's full disk encryption technology. It may also be used for storing sensitive information related to mobile payments and for creating protected hardware components, such as a secure keypad that only communicates with the secure world, such that if the operating system is compromised, perhaps elements of PIN entry may remain secure. Additionally, many vendors choose to implement secure boot in such a way that it relies on software programmable fuses, such as Qualcomm's QFuse technology. And because TrustZone has the ability to read and write these software programmable fuses, frequently TrustZone plays some sort of role, either directly or indirectly, in actually managing secure boot itself on mobile devices. And then finally, a number of device manufacturers, most notably Samsung, have implemented their own security solutions that rely on TrustZone. As part of their Knox security suite, Samsung has implemented TIMA, which is the TrustZone-based integrity measurement architecture. Among other things, this subsystem runs in the secure world and periodically scans the device kernel in memory to verify that no tampering has taken place. And if it detects any sort of compromise or suspicious activity, it'll raise some sort of security exception or potentially reboot the phone. Prior to today, there's actually been very little public research on attacking TrustZone. Thomas Roth gave a talk in 2013, I believe at CanSec West, called Next Generation Mobile Rootkits, in which he described using TrustZone as a platform for surreptitiously spying on a user, and noted that it's a particularly good choice for this kind of activity because even if a user has the ability to control the kernel does not have the ability to look into TrustZone to see if any sort of malicious activity is going on. And while he described the existence of specific vulnerabilities in TrustZone as a potential vector to install such a rootkit, to my knowledge, he didn't talk about specific vulnerabilities, much less exploitation of them, which is what I'm going to be mostly focusing on today. Next, also in 2013, I published a post on the Azimuth security blog called Unlocking the Motorola Bootloader, in which I described a Motorola-specific TrustZone vulnerability that allowed me to defeat secure boot on these devices. Next, a number of exploits published by the sort of Android rooting and modding community, like XDA developers and the like, specifically for HTC phones, have used TrustZone-related attacks in the past, but these exploits have all been not only undocumented but obfuscated and not publicly analyzed, so very little public insight has been gleaned by this research. And then most recently, perhaps a month or two ago at Recon, Nathan Keltner and Charles Holmes gave a talk called Here Be Dragons, where they described vulnerabilities specific to HTC's TrustZone implementation. And I should thank these guys for communicating with me while they were doing this research and sharing their findings. So looking back at the previous couple slides, we can begin to paint a picture of why this may be an interesting research target. Firstly, it's clearly a high-value target to a number of different parties. You have content providers who rely on TrustZone to prevent piracy of their media. You have OEMs like Samsung who implement security services to protect their users and gain an advantage, especially in enterprise markets. And then we have users who rely on the same security features to protect themselves, and as is the case with groups like XDA developers and other ROM and rooting enthusiasts, frequently want to defeat TrustZone to defeat things like secure boot, to install their own software on their phones. This, coupled with the fact that there's been very little public research and as a result very little public scrutiny to support the sort of lofty claims of security that marketing literature has put forward, makes this a compelling target. So for this research in particular, I chose to focus on Qualcomm's implementation of a TrustZone kernel, which is called the Qualcomm Secure Execution Environment, or QSEE. And the reason behind this was fairly simple. Qualcomm enjoys a sort of majority market share, especially among mid to high-end Android phones, especially in North America and Europe. Basically, if you have heard of a flagship model by Samsung, LG, Motorola, HTC, and it's for sale in Europe or North America, chances are it's running a Qualcomm chipset and as a result is using Qualcomm's TrustZone kernel. So it's by far the most popular TrustZone kernel in the market today. For actually performing this research, the toolchain requirements are fairly minimal. Obtaining TrustZone images is incredibly straightforward. If you just spend the time Google searching, you can find huge archives of firmware images for dozens and dozens of Android devices. And frequently these are just simple archive formats like tarballs or zips. And you can pull out the TrustZone images directly from those full firmware file formats. Additionally, if you have root access on a live device, you can use a Linux utility like DD to simply pull the TrustZone image directly from disk. And once you have a TrustZone image in hand, analysis was really just as straightforward as pulling up your favorite disassembler, in my case IdaPro, and going to work reverse engineering. Now, earlier TrustZone images actually rely on a proprietary Qualcomm header format, which is a 40-byte header that dictates where in memory certain sections of TrustZone are loaded, which is fairly easy to sort of guess the meaning of, and I think some people have gone out of their way to provide third-party documentation on that. But nowadays, the more recent TrustZone kernels are actually ELF binaries, so you can load them up in IdaPro and it will handle loading things in memory for you, and then you can go to work. Now, I find it's a useful exercise whenever beginning any sort of vulnerability research endeavor to enumerate the attack surface that's present on the target. In this case, by far the most lucrative piece of attack surface was a software exception mechanism called the Secure Monitor Call, or SMC. So SMC is an ARM instruction, which is a privileged instruction, meaning it can only be executed by the kernel, that is somewhat analogous to a system call. So much like a normal application will issue a system call to request the operating system kernel provide some sort of service for it, the operating system kernel can issue an SMC request to request that TrustZone do something on its behalf. Additionally, TrustZone may be tasked with handling various hardware exceptions, such as interrupts and external aborts, but this is a much more narrowly defined interface, so I suspect it's less likely to have vulnerabilities. Qualcomm's implementation doesn't rely on this so much, but other TrustZone implementations, most notably MobaCore, rely fairly extensively on shared memory segments to pass information back and forth between the secure and non-secure worlds. So that's a potentially interesting target on those implementations. Next, it's possibly interesting to note that the contents of the disk, eMMC flash on the devices, is a potential attack vector to attack the secure world. When you consider the fact that in many cases TrustZone will actually read the contents of disk and do some amount of parsing, for example, to verify the contents of disk for secure boot, any vulnerabilities in that reading from disk and parsing could potentially be exploited by pathological disk contents to exploit these vulnerabilities. And then finally, there may actually be vulnerabilities in the individual trustlets, these trusted applications that are frequently authored by third parties. And I did spend some time looking at a number of these and found that there was a high amount of sort of low-hanging fruit, somewhat trivial and easy to exploit vulnerabilities in these trustlets, probably because the vendors that are authoring them likely don't have the same kind of security engineering culture as an organization like Qualcomm might. But unfortunately, or fortunately, these trustlets are isolated from one another on later TrustZone kernels. So even if you're able to compromise an individual trustlet with a vulnerability in it, you don't necessarily gain access to other trustlets, much less the TrustZone kernel. So it's a somewhat more limited attack. Having enumerated this attack surface, I wanted to be clear about what my sort of assumptions were about the capabilities an attacker would need to possess to perform an attack on TrustZone. So for today's research, I wanted to assume that we had arbitrary code execution on the device already. And this is really just for practical reasons because there's essentially no remote attack surface for most real TrustZone implementations. It's very difficult to imagine a sane use case where the TrustZone kernel on a phone needs to receive data directly remotely. That having been said, we also want to assume that the attacker has kernel privileges on the device. Whether that be because the attacker is the owner of the phone who actually physically owns it, or an attacker that has gained access to a device and escalated privileges via a kernel exploit, which is a somewhat well understood process. The reason for this assumption is that we really want the ability to issue these SMC instructions because this provides by far the broadest attack surface. And if we don't have kernel privileges, there's practically no ability to interact with TrustZone at all. You can sort of imagine a scenario where some sort of unprivileged application may be able to request that a privileged application make a call to TrustZone on its behalf that exploits a vulnerability in TrustZone, but as you can probably guess, this is seeming less and less likely to happen in real life. The last thing that's important to note is that in this threat model, crashes and denial of service bugs in TrustZone are not considered security relevant to us. Because we're assuming that we already have the ability to run code as the kernel, we already have the ability to not only reboot the device, but also probably do irreparable harm to it. So having the kernel trigger something that causes TrustZone to crash doesn't actually result in gaining any sort of privileges that we didn't already have. Next, we're going to be moving on to the actual implementation details of QSEE itself specifically. So QSEE as a TrustZone kernel is closed source. So all of the information presented here on QSEE has been reverse engineered in IDA Pro. However, the kernel side of things that actually communicates with TrustZone is open source as part of the Code Aurora Forum GitHub tree that's available online. So actually looking at these kernel drivers and how they talk to TrustZone gave some insight on some of the ways of communication. So the interface that Qualcomm provides as a kernel driver is called SCM, which is the Secure Channel Manager, which I found very confusing considering the fact that it actually uses the SMC instruction as the way of communication. And the way it issues these requests is via two calling conventions. There is a Call-by-Register convention and a convention that relies on using a request and response structure. So the Call-by-Register convention is fairly straightforward. In this convention, the kernel loads the R0 register with this ORed value that contains the SMC command number, which you can think of as a system call number. It's just sort of the ID of the command that the kernel is requesting of TrustZone. Various flags, and then the number of arguments that it should expect. And then the individual arguments to the SMC request go in subsequent ARM registers, R1, R2, and so on. Much more interesting is the second convention, which relies on these command structures. So in this convention, the R0 register is loaded with the physical address corresponding to a command buffer, and then the SMC instruction is issued. Now, these command buffers feature a request header, a request buffer containing essentially arbitrary input data, a response header, and then a response buffer containing arbitrary output data. The request header is described by this SCM command structure in the kernel tree that's available as open source. And it features a length field, which describes the length of the entire command buffer, a buffer offset field, which is the offset of the input data from the beginning of the command, the response header offset, which is the offset of the response header from the beginning of the command, the ID, which is this ORD value that encapsulates the SMC request number, flags, and so on, and then the actual input data. And this is expected to be populated by the kernel before it issues the SMC request to TrustZone. Then, when TrustZone has finished processing the request, it is expected to populate the SCM response structure, which contains a length field, a buffer offset field, which is the offset from the beginning of the response header to the output data, and then this is complete flag, which is just set to 1. Now, because this request structure is populated entirely by the kernel, and in our threat model, from the perspective of TrustZone, we're considering the kernel as untrusted, as a potential attacker, then TrustZone needs to perform some sanity checking or validation of this request structure to ensure that the kernel is not trying to trick TrustZone into doing something malicious, into perhaps writing into secure memory and corrupting something. Now, in particular, there are 5 sanity checks that they perform to make sure that the request structure is sane. The first of these is that the length of the command buffer is greater than or equal to 16, which is the size of the request header. Next, they confirm that the buffer offset, which is the offset from the beginning of the command buffer to the input buffer, resides somewhere inside the command buffer. All of these make sense so far. Next, they check that the buffer offset is greater than or equal to 16, which is the size of the request header, to guarantee that the input data doesn't overlap with the request header. Next, they confirm that the response header offset is less than or equal to the command length minus 12, where 12 is the size of the response header. So this is a check to actually guarantee that the response header fits inside the command buffer. And then finally, perhaps most importantly, there is an invocation of a function that I called QSEE is non-secure memory. There's no symbol support available in TrustZone, so all of these functions I just named appropriately for convenience sake. And what this function is designed to do is guarantee that the entire command buffer being provided by the kernel resides in non-secure memory. And when you think about it, this makes sense. This is an important security assumption. Because if the kernel were to, for example, provide an address residing in secure memory and then issue an SMC instruction, it's possible that TrustZone would then go ahead and perform operations, either read from or write to that memory in secure memory, and potentially allow for a compromise. The way these secure memory checking functions work, they're actually a series of functions that are designed to check if a range of memory is considered protected. And the way they implement this is entirely in software, using a hard-coded list of regions with various flags that indicate various memory attributes. So when this top-level secure range checking function is called, QSEE iterates over this list of regions and checks that the specified region doesn't overlap with anything that's considered protected and returns a value appropriately. And this is somewhat analogous to the Linux kernel's use of the access OK macro, for those of you who are familiar with Linux programming, where the question that's being asked is this memory safe for TrustZone to operate on? Or is the kernel potentially trying to trick TrustZone into doing something malicious? Now, this is pseudocode that I put together that roughly approximates what goes on when QSEE performs these checks. You have this top-level function, QSEE is non-secure memory, that takes arguments of an address, meaning the start of the region that's going to be checked, and a size field indicating how big the region that they want to check is. Next, they call down to a secondary function that I called QSEE range not in region, where they provide the address of this linked list of protected regions that resides in secure memory. And then they provide the address again, and then they attempt to calculate the end of the region that they want to check by adding the address plus the size of the region. Now, interestingly, in this function, this secondary function actually checks that if the end of the region that's going to be checked is less than the start of the region that's going to be checked, they assume that the caller has made some kind of an error, and they reverse the arguments for you. And this immediately jumped out at me as something that's potentially a very bad idea. So some of you probably have already spotted the bug, having looked at that code. Just in case, a quick review of the concept of an integer overflow. So on ARM devices or other 32-bit devices in general, integers are represented as 32-bit numbers, which is the maximum size of a single standard register. So integers have a maximum range of 0 to hex FFFF, which is 2 to the 32 minus 1. So during arithmetic operations, if this maximum value of an integer is exceeded, then the resulting value will wrap back around to 0. So in this case, if you add the largest integer possible with 1, you get 0. So applying this idea to the invocation of the secure memory checking that's used to validate this SCM command structure, they invoke this is non-secure memory with a kernel provided or attacker provided, in our case, address of a command and the length of that command. Now what happens if the address of the command plus its supposed length, both of which are attacker provided values, is greater than the maximum representation of a 32-bit integer? Well, in this case, the answer is fairly clear. So this secondary function will be called with the start of the command buffer, and then this address plus size field will wrap around and result in an address that is lower than the starting address. And then, in this secondary function, end will be less than start, and it will reverse these arguments. So this allows us to create a pathological command buffer that does evil things. So in this example, say that this region here is the actual QSEE image, which is secure memory. It's considered protected. Now, we can place our command start perhaps over here, and then provide an extremely large command length such that the sum of the address of the command and command length wraps all the way around and ends up here. Then, in the range checking function, these arguments will be reversed so that the range that is checked to guarantee that it is in non-secure memory is this region here, rather than the region starting at command and extending all the way to the end of memory, which is what it intended to do. As a result, we can actually set a response buffer offset to be anywhere in this region of memory, including on top of the QSEE image itself. So looking through these 5 sanity checks once more, it's clear that with this pathological command buffer, all of these conditions are satisfied. The command length is significantly greater than 16. The buffer offset is less than the command length. The buffer offset is significantly greater than 16. The response header offset is our sort of arbitrary offset to point into the secure memory, is less than our command length, which is really massive. And then because of this integer overflow and the subsequent reversal of these start and end values for range checking, this check that is designed to guarantee that this range is non-secure returns true, even though it clearly should be returning false. Now, the result of this bug is that we can craft an SMC request that exploits this integer overflow and causes QSEE to write a response header to arbitrary secure memory. And this is clearly a serious vulnerability that can result in compromise. And the goal from this point forward is to achieve arbitrary secure code execution on these devices. The first thing to look at is clearly what gets written to a response header. What kind of data can we cause QSEE to write to arbitrary secure memory? And it turns out that the response header is hard-coded in all cases. It writes the length as 12, which is just the size of the response header. The buffer offset is 12, and then this is complete is set to 1. So the final result is that we can write these 3 words, 12, 12, 1, to arbitrary secure memory. Exploiting this is somewhat of a challenge, but a few things make it easier. The first of these is that the memory layout of QSEE is almost entirely known to the attacker. Because the TrustZone image sits on disk, and we're assuming that we're running as the kernel, we can read that image from disk, And because it is loaded at a known constant physical address in memory, we essentially know we know the entire layout of the TrustZone image in memory, even though we can't explicitly read the secure memory where it resides. Next, it's helpful that most of RAM is actually non-secure memory, so we have a somewhat large sort of scratch pad to work with when we're trying to do things in memory. Now, the sort of classic approach that you would take if you were approaching this like a traditional kernel exploit may be to find some sort of function pointer that lives in secure memory, and then use our write primitive to overwrite some of the bytes of that function pointer so that it now points to an address residing in non-secure memory. Then we could put a payload at that non-secure address and cause that function pointer to be invoked by TrustZone. And then the result would be TrustZone running our non-secure payload, and that would be victory. Unfortunately, this doesn't actually appear to work. So I suspect that QSEE actually has some sort of mechanism in place that prevents TrustZone from executing code from non-secure pages. Sort of analogously to how user-land applications have NX or DEP, or more recently, the Linux kernel on ARM or x86 have PXN and SMEP, respectively. And I suspect it may have to do with the XPU, which is the memory management component that handles marking regions as secure. But this is an undocumented black hole. It's very difficult to understand what's going on here, and I don't have the capabilities to look at the hardware close enough to actually understand what's going on. So this is the part of the talk where I coyly ask if there are any Qualcomm or ARM employees in the audience who want to answer this question as to whether this is the case, but I'll let them off the hook because I assume that they can't say. So we need to take another approach to actually gaining arbitrary code execution, because it's clear that, at least from experimentation, it's not going to work. We're not going to be able to cause TrustZone to execute non-secure code. We need to find a way to cause TrustZone to execute secure code in a way that allows us to win. Now, the fact that this is a 12-byte memory write where we don't control the contents makes exploitation somewhat difficult. So the first thing that's a little bit tricky is that because it's a 12-byte write, if we want to overwrite one word in memory, then we're necessarily clobbering two adjacent words to that, which could potentially lead to instability depending on what the target is. And then additionally, probably more importantly, we have very minimal options in terms of what we can do because we have this very limited vocabulary of what we can cause to be written in secure memory. You know, we only have zeros, a 12, and a 1. And that's fairly limited. So the challenge here is actually coming up with a way of using this first exploit primitive to build a more flexible one that allows us to achieve our goals. Now, revisiting these secure memory protection functions. So we recall that QSEE checks the status of memory regions by iterating over this linked list, which has hard-coded regions. And each of these regions is encapsulated by a structure that is similar to this. This is just what I've reverse engineered. Each region structure has an ID, which is just an incremental identifier, flags that indicate the actual protection attributes of that region, and then the start and end of these regions. So what I came up with was that we can actually use our 12-byte write to overwrite the flags, start, and end addresses of the region entry corresponding to the QSEE image. So the result of this is, anytime QSEE goes to check the safety of a pointer provided by the kernel to guarantee that it's safe for it to assume that it's non-secure and that it can read from it and write to it without consequence, if that pointer resides in the address space reserved for the QSEE image, it's going to say it's fine, it's safe. And at this point, this gives us the ability to write to arbitrary secure memory with any value that QSEE writes as output at any point. Here we can basically choose a new write primitive. We've expanded our vocabulary for what we're able to write to secure memory. So at this point, I enumerated all of the SMC handlers, eliminated those that don't write any output at any point, and now we've got a list of things that we can write to arbitrary secure memory, and we can, depending on how we design the rest of the exploit, just pick the one that suits the task at hand. And now the only missing piece here is actually finding a way to win. You know, we have a more flexible write primitive, but how do we actually get code execution? Well, revisiting how QSE actually handles SMC instructions. So when an SMC instruction is issued, QSE will parse the command structure, and it will iterate over a table with these variable length entries, where each entry corresponds to an SMC handler, sort of like a system call handler, where each entry contains an SMC number, which is just the identifier of the SMC request, a pointer to a string describing the handler, which was incredibly useful when trying to figure out what each of these handlers actually did, various flags, and then a function pointer to the actual function that gets invoked by QSE when this SMC request matching this ID is issued, a number of arguments field, and then a variable length array whose length depends on this number of arguments field, because this variable length array is actually contains one entry for each argument, and each entry corresponds to the length of each argument. So I ended up using the ability to write essentially arbitrary data to arbitrary QSEE memory to create what I call an SMC table extension attack. So I actually use arbitrary secure memory to modify the number of arguments field in one of the SMC tables. Table entries, rather. Now, what I did was I actually expanded the size of one of these SMC entries so that it's particularly massive, and that when QSE is iterating through this table and tries to find the location of the next SMC entry, it will actually jump way into non-secure attacker-controlled memory, at which point we can put a fake entry there. And at this point, we control an SMC handler. We can make up an SMC ID, point the function pointer anywhere we want in secure memory, and craft any sort of set of arbitrary arguments, and basically call any function in TrustZone at whim with any arguments we want, which, in my opinion, is a fairly elegant way to gain total control of TrustZone. At this point, we have arbitrary TrustZone code execution, and we have won. One of the fun things you can do is actually find the memcopy implementation in the TrustZone kernel and actually just invoke that to copy all of secure memory to a non-secure buffer. So this would allow you to steal any DRM or secure key storage related stuff. So any sensitive data stored in secure memory now becomes available to the attacker. You could disable TIMA. You could disable any piece of security-related functionality in TrustZone. You have full control. And then perhaps the flashiest thing you can do is invoke OEM-specific functionality to do things like permanently unlock a bootloader of a device. So that's what I'm going to do right now. So I have on stage a Verizon-branded Moto X. So the way that Motorola implements secure boot is by featuring a manufacturer-sponsored mechanism to unlock the bootloader, which would allow users to install custom operating systems and so forth. And the way they do that is the user actually sends Motorola a request token that they got from their device. If that token matches a device on an approved carrier, then Motorola will send a token in response that the user can then issue to the bootloader, and the bootloader will make a request of TrustZone to unlock permanently by blowing a Q fuse. Now, and for Verizon and AT&T, they just won't give you a response token back, so there's no way to unlock your bootloader, except if you have a single TrustZone vulnerability, you can actually do it yourself by just invoking the functionality that they would do if you gave them the response token. So here I've got, we've got a Verizon Moto X running Android 4.4. As you can see, it is not unlocked, and the warranty is still present. So I need to continue booting. So this will take just a moment. So this is an incredibly risky demo because, first of all, it's live, which is always a bad idea. But additionally, you can only do this once to a phone because you're permanently blowing a fuse. So I obviously have never tested it on this phone, so who knows what's going to happen. It's I think it's the second riskiest thing I did in this talk. The first was using OpenOffice to make my slides. Okay, so just using ADB, we have a shell. I'm going to use an implementation of the recent Linux Futex vulnerability to escalate privileges to root. And then I'm going to cross my fingers and hope that this works. Well, it didn't break. And we're going to pull up the bootloader variables again, and we can see that the device is now unlocked. So at this point, you can actually use fastboot, which is built into the bootloader to flash any software you'd like on this phone. So as far as I know, this is the only, or one of the only Verizon Moto X's in the world that's unlocked. So a few lessons can be learned from this research. One of the most practical ones is that analysis and exploitation of TrustZone was made much easier due to the fact that there's no sort of protection or encryption of the TrustZone image itself. You can compare this to iOS, where TrustZone is actually stored encrypted on disk, and as a result, without either a leak of firmware from Apple or exploiting TrustZone itself, which is basically impossible if you've never had a TrustZone image to analyze in the first place, you need an iBoot vulnerability to actually gain access to a decrypted TrustZone image to analyze in the first place. Next, parsing of complex data structures, in this case, these command buffers, seem like a fairly obvious point of failure. So as a vulnerability researcher, places like this are really good targets for scrutiny. The next thing is, as a researcher, it's important to learn to develop a spider sense and learn how to trust your gut. If it looks sketchy, it very likely is. In this case, the minute I saw in the assembly code this reversal of arguments in the case of an erroneous call, that seemed to yell out at me as something that was potentially bad, even though I didn't know immediately what that would be, and it turned out to be a very critical vulnerability. Next, just looking at, for example, bootloader design, single points of failure are a bad idea. When you look at Samsung's implementation of Secure Boot, for example, there's no single point of failure. There's no off switch that allows you to exploit something and unlock the bootloader. In contrast to Motorola, which made a design decision that makes it easier for them, because now they don't have to ship different software or hardware for different carriers, but they also included a mechanism by which any single TrustZone vulnerability will result in a permanent unlock of Motorola bootloader, which is great if you're like me and you like installing stuff on your phone, but not so good for Motorola's customers. Next, I think the basic idea and design of TrustZone is excellent. Having hardware enforce security boundaries and a minimal core operating system component that is considered trusted is a great idea. But unfortunately, what I think we've been seeing here is that so many vendors are so jazzed about TrustZone that there's been so much feature bloat that the attack surface in TrustZone itself has widened substantially. And that sort of eliminates one of the big advantages of having a system like TrustZone, which is designed to be small. And then finally, I think everyone in here already knew this, but the best marketing team in the world will not change the fact that software is written by humans and humans occasionally make mistakes. So despite the fact that something may be billed as 100% secure, and no joke, I have actually seen that in media reports about TrustZone, that does not mean that it's not worthy of attention and scrutiny and that there aren't bugs there. That's it. So I had a contact slide, but that's all right. That's the end of my talk. Thank you.